So we have a problem which says that we have from rest, right? A car is accelerating at 8 meters per second squared and for 10 seconds. So we need to find out position of the car at the end of those 10 seconds. So where is it located in relation to its original point? And what is the velocity of the car at the end of the 10 seconds? So oftentimes, you don't have to solve the problem head on. You don't have to go A and then B. Oftentimes, you can start with B and then go back to A. It's a matter of choice. It's a matter of like how comfortable you feel with the formulas. And if I compare that to swimming, like some people swim like this, like dogs. Some people just know freestyle or something. But some people have like, they can swim backstroke, breaststroke, butterfly, so they're more versatile. So if you're more versatile, it's almost always on this level. Doesn't matter from which level, from what question you start. Okay, does it make sense? So here I prefer to start with the second question because I immediately see that we can find velocity of the car at the end of 10 seconds. Now, oftentimes, almost always actually, you should draw a little diagram. So I'm going to draw a little car, and this will help me imagine, you know, that's the car. It's going to go this way for 10 seconds. And acceleration here is A equals 8 meters per second squared. Okay, so I basically put down the information that is available to me. Now, there's another information that is not explicitly stated, but it says that the car starts from rest, which means I know its initial velocity. Initial velocity is equal to 0 meters per second. So always remember, you have to use a little bit of common sense. If it says like airplane is taking off, you know, obviously its initial velocity will be 0. Or the car is coming to stop. That means final velocity will be 0. So you have to use the cues, the words that carry that information, and translate them into the mathematical symbols. Okay, so we know acceleration is equal to v final minus v initial over delta t, right? It always makes sense to use a little bit of algebra to solve for the unknown first, and then plug in the numbers. I know many of you learned it backwards. You plug in the numbers and then try to solve for the unknown. But believe me, like when you do that, you carry a lot of weight around, all the numbers, you have to move them around, do a lot of computations. Algebra allows you to avoid that, minimize the work. And since some people argue that they don't want to work too hard, you know, try to use a little bit smarter ways to minimize your work instead of complaining. So this is what we get for the V final, a useful expression to be familiar with. You don't have to memorize it, but you should be able to figure out where it comes from. It comes from the concept of acceleration. So now what we do is we just plug in the numbers. 8 meters per second squared. Now, I will ask you to plug in the units as well, like you did in chemistry, and take care of the units as well. So here, second here on the time, and one of the seconds here will cancel out. So this way we can eliminate or reduce the expression, dividing both 10 seconds and a second squared by seconds. And then our final answer here will be 80 meters per second. And the unit kind of makes sense. It tells us that that's the meters per second, that's this velocity unit for the velocity, right? Also, it's not obvious, but we have to keep in mind the sign here is plus. So it implies the car has been moving forward and it has not changed its direction. So it's still moving forward, which kind of makes common sense, right? Should make some sense. So we answered the B question because it was immediately available. We could use this equation. Now we want to know the position of the car at the end of 10 seconds. Now we could have gotten A right away if we used the equation that I'm about to write right now. So D equals to V initial times delta T plus 1/2 A delta T squared. So whenever you have a question, like a problem, physics problem, and you want to find something, you have to always kind of lay out what's given, what you know, and what you don't know. So what I'm going to do, I'm going to underline the quantities that are known to us. Initial velocity is known, time is known, acceleration is known, time again is known, and this is the question mark. So this is a perfect formula that allows you to find what's unknown. There's only one unknown, right? And whenever we have one unknown in an equation, usually we can solve it quite easily. So we plug in the numbers. I'm gonna write to the right here. So this is 0, right? The V initial is 0, so that drops out. 1/2. Acceleration is 8 meters per second squared. Times, be careful when you square a physical quantity, here it's time, you have to square the units as well. Now, when we do that, we're gonna end up with this. So D equals 2. I'm gonna drop 0, I'm gonna write 0. 1/2 8. So I'm not rushing to calculate, to compute. Okay, I wanna see if I can like play with this a little bit and then reduce the amount of work. So this is 100 seconds squared. So now everything is laid out, so we can actually now try to reduce the expression, right? Again, it's a matter of choice. You could have like canceled 8.5, reduced it right away. I just chose it to do it in the next step. So here we have 8 and 2, so this becomes 4, and thus the displacement will be over here. I'm gonna write up here. Displacement will be 400 meters, right? So that's the answer for the A question. Okay, so we could have gotten A first and then switched to B. It doesn't really matter. Okay, now I'll show you one more way to solve for A. If acceleration is constant, then we can use the fact that the average velocity will be average of the initial and the final velocities. So this thing is valid only when acceleration is constant. So now let's figure out average velocity. Initial velocity is 0, final velocity we already found in B, for question B, it's 80 meters per second. Divided by 2. So obviously this is 40 meters per second. Now I can use the general expression, the general equation that I mentioned before, that is always true. Average velocity times delta t will give us displacement. So these are 2 steps, but each step is quite easy. You can do it in your head, and you don't have to square numbers. If numbers are inconvenient, it'll take a little bit more time. These are a little easier steps. So sometimes 2 steps, taking 2 steps takes less time, right? Than one big jump. What if you don't get, what if you don't get there? What if it takes too much energy? So again, kind of budget your energy, budget your time, depending on the problems, and try to see which way it is easier. By easy, I mean more efficient, because sometimes people choose easier work and they end up doing a lot of work, tedious work. So we want to kind of get it done quickly and efficiently. So from here, we see the total displacement will be equal to 40 meters per second times 10 seconds. Seconds, again, conveniently cancel out. So answer is 400 meters. So I can say that this is total distance because we are only interested in that interval of time. And for that interval of time, that is the total distance. What happens afterwards, it doesn't really bother us. This is the way physicists, scientists usually think. They take a chunk of time and they thoroughly analyze events happening in this time. And if they completely understand that, they don't want to be bothered about everything outside of that, okay? But if they find something happening here and something is like affecting the motion, like in this case, right? And it's outside of the picture, then it makes sense to expand the problem. Usually we want to confine the problem so that there's less work, there's less complexity, which means our answers are going to be probably correct. Does it make sense? Right? So if you take a real complicated problem and try to solve it, you may end up wasting a lot of time. If you break it down to simpler problems, you may actually end up moving faster. So that's the reasoning for that. Any questions about this? So I see no questions, right? All right, so we're gonna go on to the next problem then. Next slide. So let's see if we can do this. Do you guys see the next slide? And the text there, right? Okay. So again, let's tidy up a little bit. Okay, so this problem is slightly different because we're given initial velocity and it's also given in kilometers per hour rather than meters per second. So we always want to get to the same units, right? It's the same issue like when you go to buy something, say in a different country, oftentimes you have to use a different what's it called, currency, right? You have to convert. If you don't convert it, then they won't accept your payment, and then there's no transaction. So in a similar manner, we have to convert everything to the same unit, and we're going to switch to meters per second. To do so, we're going to look at what kilometer is and what hour is. So if I have 1 kilometer per hour, I can convert this into 1,000 meters per 3,600 seconds. And then if I simplify this, right, moving decimal points and everything, this will become 1 over 3.6 meters per second. So if I want to convert kilometers per hour, I'm gonna divide that number by 3.6. Let's say we have 72 kilometers per hour. I want to convert to meters per second. So I'm gonna do is 72 divided by 3.6. So that's a conversion coefficient, right? You can always write 1,000 meters, you can always write 3,600 seconds, but I'm showing you, like if you appreciate it, you can use it. Shortcut is dividing the kilometers per hour by 3.6. So this ends up being 20 meters per second. Okay. Now, what if you want to convert meters per second to kilometers per hour? Sometimes you have to do that. So a meter is 1 over 1,000 kilometers of a kilometer, and a second is 1 of those 3,600 of an hour. So we flip everything upside down, like dividing fraction by a fraction, right? So we end up with that, which means, and then this will be kilometers per hour, right? So the coefficient here becomes 3.6. So if I want to convert meters per second to kilometers per hour, then we can just multiply by 3.6. For example, you can easily run at about 5 meters per second. Easily. And if I multiply by 3.6, this will give me 18 kilometers per hour. Okay, 18 kilometers per hour. So in 2 hours, you can cover 36 kilometers, right? So you can run a marathon, I guess. 42 kilometers is just slightly more than 36 kilometers. So that's a reasonable speed kind of for a human being to run for a little bit of time. Okay, so let's get to the problem. Initial velocity is given at kilometers per hour, so we're going to convert to meters per second. So V initial is equal to 20, and we need to divide this by 3.6, right? Like that. So if you use your calculator, you can figure it out. I'm going to try to estimate this. So roughly, what is it? 5, a little bit over 5, 5.2. Can you use your calculators and see what you get? $5.5. Okay, so we're gonna get 5.55. Now it makes sense to carry like multiple decimals because you don't want to end up with rounding error. If you're using calculator, do not round the number for the next calculation, just carry it over. Okay, so it's asking you what's the position of the car at the end of 10 seconds. So now the formula for that is initial velocity times delta t plus 1/2 a delta t squared. So we're going to use this formula. And nothing says about changing direction, so we make a simple assumption that in this case, the vehicle is going in the same direction. So here we go. D equals to initial velocity is 5.55 times 10 seconds. So this is meter per second times second plus 1/2. Acceleration is 8 again. Meters per second squared times 10 seconds squared. So when you do calculation, you will end up 55.5. So I'm going to just keep 1 decimal meters. Plus, we know this one will be 400 from the previous problem. So that means the answer to the question is for the question A. It's 455.5 meters. Okay, 1 or 2 decimals are more than enough for the most of the problems. If the question says round to the nearest number, whole number, blah, blah, then you just follow that instruction. If it doesn't say, if you left 1 or 2 decimals, that's more than enough. Okay, so questions? Yeah.
So you know where you did the V initial equals 20 times 1 over 3.6? Why did you do that? A little bit confused on that.
So as I mentioned over here, we need to convert kilometers per hour. Can you mute the microphone? Arian, could you? Yeah. So kilometers per hour, but everything else given in meters and seconds, right? So we need to convert kilometers per hour into meters per second, right? So we use the same units for velocity and for acceleration and for time. So the conversion coefficient, as I explained before, is you divide the kilometers per hour by 3.6. Example was given to 72 kilometers per hour. If you divide by 3.6, you get 20 meters per second. A car going about 55 miles per hour, 50 miles per hour, will be traveling 20 meters every second. Okay? So that's a conversion. Once we convert that, once we learned about this conversion, we use that conversion coefficient to find initial velocity in meters per second. And then thus we can plug this into the equation because now we have all the same units. Meters are here, seconds. Make sense? So now we operate only with the same units and we can add them. Think about it this way. You can add like terms, right? If this was kilometers, this was meters, we would not be able to add like terms. Okay, I see some people leaving. 1 second. 1 second. I see some people leaving and coming back. Do we have like internet problems? If you do, please text me, let me know. Because I already took attendance and you will be marked absent if you're joining class later. Okay, Camilo or whoever that is. Arian, what was your question? That's it? Okay. All right, let's get to the next part. What is the velocity of the car at the end of 10 seconds? So we know this is easy because we did this before. So we're just gonna straight away plug in the numbers. So B, initial velocity, final velocity equals to V initial plus A delta T. V final is equal to, initial velocity was 5.55 meters per second plus 8 meters per second squared times 10 seconds, right? I don't really need parentheses, but whatever. So crossing out this second and this second over here gives us meters per second for the units. So 80, V final is 85.55 meters per second. And that's the answer for the second question. So for the classwork, you will get similar questions. So to continue the classwork, similar questions, and just use the samples as examples of problems. So I will be posting the slides on Google Classroom, and I'll also probably add on a few videos in addition to the video that I have today. The one I have today will be posted just a little bit, but it has to be like processed or something, converted or whatever. Any questions before we adjourn? We have about 3 minutes left.
Is the standard unit for acceleration meters over seconds squared?
Yes, because the formula says delta V over delta T. So if we change the velocity, right, and divide by time, so we have meters per second, that's the unit for the velocity. We divide by seconds. So you're dividing meter by second squared. So we say this is the unit for acceleration. So the brackets usually stand for units. So units for acceleration are meters per second squared.
Okay, thank you.
Mm-hmm. Okay, questions. Don't be shy. Okay, so I'm going to stop recording this one. And